right, let's talk about acids and bases, a topic that you may have covered in quite detail in Chemistry 101 and 102. We are going to talk about it a bit in organic chemistry as well. We're going to talk about first acids and bases, the definitions of what it means to be an acid, what does it mean to be a base, and then we're going to define this quantity called pKa, which you may or may not have heard of before. We'll talk about it in a minute. We'll get there. All right, so let's start by defining a couple terms, and the first term I want to define is the Bronsted, with that little O with the line through it, Lowry acid. The Bronsted-Lowry acid is simply a H+, which is a proton, donor. So according to this definition, an acid is something that donates a proton. And then, probably remember, there is the Bronsted-Lowry base. The Bronsted-Lowry base accepts a proton. Okay, so let's take a look at an example of an acid-base reaction and see if you can identify the acid and the base. Okay, so we'll have HCl plus H2O. And I'll draw in some lone pairs, why not? Feeling fancy today. And we'll draw an equilibrium arrow to show that these acid-base reactions are easily reversible. And the products of the chloride ion plus the hydronium ion. Okay, that's an example of an acid-base reaction. So let's see if we can identify who is our acid and who is our base. So all you need to do is look at the starting materials. Remember, the starting materials on the left side. And take a look at, let's say, HCl. Now, in the course of this reaction, does it gain or lose its H? Well, if you look at HCl, it becomes Cl-. So that means it lost its H. If it loses its H, it's an acid. So we'll say acid, and that makes sense because it is donating its proton. And then let's take a look at the H2O. The H2O here is gaining a proton. It's going from H2O to H3O, so it is the base. It is a proton acceptor in this case. Of course, you need to assess the role of each reactant in every acid-base reaction independently, meaning in sometimes water could be an acid. In other reactions, it may be a base. You need to assess whether it gains or loses a proton in that specific reaction to determine whether it is an acid or a base. There's also some terms that we should know about the other side of the reaction. What the acid becomes when it loses its proton, we call that the conjugate base. And what the base becomes when it gains a proton, well, that's becoming the conjugate acid. So make sure you understand those terms, that the acid becomes the conjugate base and the base becomes the conjugate acid. All right, let's do another example. And let's say this is an example test question. Identify the acid, base, conjugate acid, sometimes abbreviated Ca, and conjugate base, sometimes abbreviated Cb. All right, let me draw out the reaction. Use those equilibrium arrows to show that it is easily reversible. These acid-base reactions are easily reversible, generally speaking. Okay, here's a reaction, so let's identify the roles of all the different players. So we'll just look at the starting materials and let's pick one of them, for example this one, and ask the question, does it gain or lose a proton? Well, look what happens to it. It is right here. Now, can you find it in the product side? Yes, it's right here. Can you see that it's gained a proton? So therefore, it's the base. And now let's take a look at the second reactant. Here's water, H2O. Can you see what's happened to it? It lost a proton. It went from being H2O to just OH. So because it lost a proton, it's the acid. The base becomes the conjugate acid. And the acid becomes the conjugate base. So we're able to label it like that. All right, so that's easy. That's easy, free points on an exam. You should have already covered this in like general chemistry. The only difference is now maybe there's some bond line structures involved, but again, all we're looking for is a proton being gained or lost, and that can allow us to identify the acid or the base. Now, one thing that we are going to really mix this up with and make this really organic chemistry flavored is on the next page, we're going to talk about something called curved arrows. Curved arrows. All right. So, one thing you maybe remember from the very first lecture when I was doing the introduction, what is organic chemistry, I made a comment that was very important, which was that all reactions involve the flow of electrons, that electrons were the most important particle. Do you remember that? Well, that could not be more true than right now. So, all reactions involve flow of electrons. And we can use curved arrows to document electron flow. In a way, the curved arrows tell a story of how electrons move in a chemical reaction. Because we as humans, we like to think of these as stories with a beginning, a middle, and an end. It's just how our brains work. We love to tell stories. So with every chemical reaction, if we can tell a story, that makes us understand it that much better. So you'll see in this class that one category of question that I'll ask you again and again and again is draw a curved arrow mechanism. Let's take a look at an example of what that might look like. Let's have a generic base, which I'll abbreviate with B. And since bases typically have a negative charge, I'll give my generic base a negative charge. You're welcome. Okay, B stands for base. And we're going to add to our base an acid. And we'll let the acid be, I'm not very creative, abbreviated with A. And what do all acids have? They have a proton to donate. So I'll draw in the proton that they would be donating. And what's going to happen in this acid-base reaction is that the base is going to take the proton from the acid. So we'll get BH. Plus, what's left over is the conjugate base from our acid, A-. So once the acid loses its proton, it becomes just A-. So now let's try and draw curved arrows to represent this process. So the base is taking the proton from the acid. So let's draw the curved arrow, which I always draw in red in this class, but you can use any color you want. We're watching the lone pair electrons grab the H, and then we also need to free the A-. So we draw a second arrow to show that the HA bond is breaking, leaving A- on its own. And so this would be a curved arrow representation of the movement of electrons in this reaction. We've actually seen curved arrows before. So let me remind you where you've actually seen these. We saw them in resonance. In resonance structures, we drew little arrows in all the resonance scenarios to show the movement of electrons. The curved arrows in resonance were simply tools and did not represent a reaction. Remember, resonance structures are not a reaction. There is no movement of electrons between resonance structures. Remember, resonance structures exist as a hybrid. Rather, all resonance structures simultaneously, they're not moving between the different forms. So in resonance form, the curved arrows were simply tools. They did not represent a physical process. That's important. But now that we're looking at acid-base reactions, we're actually looking at reactions. So reaction curved arrows do represent a physical process. And this is called a mechanism by organic chemists. This physical process is called a mechanism. Okay. So let's take a look at another mechanism for an acid-base reaction. Let's take, for example, hydroxide ion. And we'll react the hydroxide ion with acetic acid. There's acetic acid. I'll draw the lone pairs. And let's take a look at the products of this reaction. We're going to make H2O. I'll just draw H2O for short. Plus acetate ion. Okay, let's start by identifying the roles in this reaction. So take a look at our hydroxide. What is it doing? It's gaining a proton, so that means it's the base. Let's take a look at the acetic acid. It's losing a proton, so it's going to be our acid. The base becomes the conjugate acid, and the acid becomes the conjugate base. Now, to draw the arrows for an acid-base reaction, there's always two of them. Always two arrows for an acid-base reaction. Arrow number one is arrow from the lone pair of base. I'll abbreviate lone pair LP of base to the H, or proton, of acid. Okay, so let's draw that right now. We'll take the arrow starting from one of the lone pairs of our base, and it'll point towards the proton of our acid. Arrow number two, it's an arrow from proton bond to deliver the lone pair to the conjugate base. Okay, so let's draw the second arrow. It's the starting from the proton bond to the atom that the proton is attached to create another lone pair for our conjugate base. Notice that our conjugate base on this oxygen, there's two lone pairs, but after this arrow occurs, there's now three lone pairs. So that arrow represents the movement of two electrons. All right, let's take a look at a couple more examples of drawing some arrow pushing mechanisms. Let's just look at two examples here. Okay, here's the first reaction. Notice that I can put the plus signs or I can leave them out. It doesn't matter. When you draw a mechanism, typically you don't have the plus signs there because they get in the way, but you can definitely leave them there if it makes you feel more comfortable. So we can go ahead and leave them here. And we can first, what we want to do is identify our acid and our base. And so look at one of the reactants, H2O. Is it gaining or losing a proton? It is losing a proton. So H2O is our acid in this reaction. And that means our CH3O minus is our base. That means our HO minus is our conjugate base, and our CH3OH is our conjugate acid. Now we draw our first arrow. It goes from the lone pair of our base to one of the H's of our acid. And then our second arrow goes from the proton bond to whatever that proton is originally attached to in the acid to deliver that lone pair to the conjugate base. And there's our arrow pushing mechanism. Let's do another example. Okay, I'm going to draw out this example here. Okay, let's do a tricky one. It's tricky because bond line drawing. Okay, so let's identify the roles of our starting materials here. So let's take a look at this guy here. Is it gaining or losing a proton? A little tricky to tell, right? Looking at it over here, did that gain or lose a proton? Maybe let's look at this molecule. It's a little bit easier to tell. Is this molecule gaining or losing a proton? Well, we look at the product. Clearly, it's gained a proton on that nitrogen. So if it gained a proton, that means it's the base. And that means the other substance has to be the acid. The acid becomes the conjugate base, and the base becomes the conjugate acid. Okay, great. So now we know who the acid and the base is. So we know that our arrow has to start from the lone pairs of our base, but where is that arrow going to go? Which proton is actually being removed? Well, if you look at the product, you can see that we now have a negative charge on that carbon. So it must be one of the protons, the implicit protons, that was attached to this carbon. But because those protons are implicit, they're not drawn in. But we're trying to draw a mechanism. We need to now draw all the protons on that carbon. So we can look at this carbon here and see that there must be 3 implicit hydrogens on that carbon because I only see 1 bond on our bond line structure, and carbon likes to make 4 bonds. So I'll draw in the 3 hydrogens that are at that position. And I see that the base is removing one of them. So the first arrow is from the base lone pair to the proton. And then the second arrow is from the proton bond to the atom that it's attached to, in this case that carbon, to create the conjugate base and dump a lone pair there. And sure enough, that's the lone pair that we see in the picture. Okay. And then, of course, if we were going to draw in the protons in the product, which you do not have to do, but for accuracy's sake, we can. We see that it's a carbon with a negative charge. Carbon with a negative charge likes to make 3 bonds. And we see 1 bond already shown. That means that there are now 2 hydrogens implicit at that position. And now you can clearly see that this molecule lost 1 proton. There were 3 protons on this carbon, but now there's only 2. So that is definitely the acid. All right, now I promised I would define a term called pKa. And once we do that, we pretty much are done for today. So boring math time. Put on your boring math hat. Boring math time. What is pKa? All right, so let's just take a look at a generic acid-base reaction with water. So if we have HA, which is an acid, plus H2O, which will be acting as our base in this example, we will form A minus, which is the conjugate base of our acid, plus H3O plus. And we can see that the acid is donating its proton to water, which is acting like a base, gaining a proton. And if you remember back in Chem 101 or 102, I don't remember which one, I think it's 102 you learned this, you can define something called KEQ. And KEQ is the equilibrium constant for an acid-base reaction, or any equilibrium reaction. And it would be written like this: the concentration of the products on the top, so H3O plus, A minus, and the little brackets, of course, meaning the concentration. And then on the bottom, we would have the concentration of our starting materials, HA and H2O. And so if we multiply both sides by the concentration of water, we get this. KEQ times the concentration of H2O equals H3O plus times A minus divided by the concentration of HA. And so this gives us a ratio of how much of the acid dissociates and how much of the acid gives its proton. If it's a really strong acid, then Ka is going to have a very large value because the acid is going to be giving up a great deal of its protons. If it's a very weak acid, then the denominator is going to be very large because it's not going to be delivering much protons to water. So that'll make this value very small. And if you remember, this value is called Ka. So anyway, you're not going to have to do any of this math in this class. All you need to remember is a very simple fact. Very strong acids, that is acids that give up their protons very readily, have a Ka equal to about 10 to the 10. They have a large Ka. Versus very weak acids, these are acids that do not give their protons up readily. They have Kas as low as 10 to the minus 50. Now, these numbers are not very convenient, 10 to the 10, 10 to the minus 50, so instead we use pKa. So these numbers are kind of inconvenient, so we use pKa, which is pKa equals the negative log of Ka. And so this gives us a pKa scale. That ranges from about -10 all the way up to 50. And so it's a scale. Kind of like the pH scale, except this is the pKa scale. And so at -10, you have your very strong acids. Because it's the negative log, that means that when the pKa is very low, the acid is very strong because the Ka is very high. But if you have a very high pKa, that is for exceedingly weak acids. All right. And the nice thing is that pKa's are quite consistent by functional group. So if you can recognize a functional group in the molecule, you can pretty easily approximate the pKa of that molecule. pKa of a molecule is determined by functional group. And so let me list out a couple of molecules. Okay. And we'll calculate their pKa's. I'm just going to draw out a couple of organic molecules. Okay, here's 5 molecules or so. And let's look at something called the pKa table, which I'm going to provide to you so that we can look up the pKa's of all the different functional groups. So the pKa table looks something like this, and it's going to be available to you on Canvas. And you can see that it's organized by functional group. So you're just looking for the name of the functional group, and then the pKa value is right there. So like, for example, if you want to know the pKa of an alcohol, it's 16. The pKa of water, it's 16, and so on and so forth. So all we need to do is look back at our molecules, figure out what functional group we have in that molecule, and then look at our table. Okay, oops, those are the answers. Okay, this is our first molecule. It is an alcohol. We see it's an alcohol because it has the OH group. So we look at our pKa table. Alcohol pKa is 16. So we'll go ahead and write right underneath it. pKa is 16. Okay, next up we have, what is this functional group called? This is the carboxylic acid. Be careful, it's not an alcohol. It's upgraded to the carboxylic acid because of the CO double bond. We can look at our pKa table, and there's the carboxylic acid. It has a pKa of 5. What functional group's in this molecule? Pretty much nothing. It's just a boring alkane. That's on our pKa table too. Alkanes are very, very low acidity. They have a pKa of 50. Now, you may be wondering, do you need to memorize the pKa table? I strongly encourage you do. I strongly encourage you actually memorize all the values on the pKa table. Now, of course, in the exams, those are open notes, so I can't really control for that. But I encourage you to memorize the pKa table. There's not that many. All right, what functional group do we have here? Do you remember what this is called, the SH group? It's the thiol. We look at our pKa table. I'll look under sulfur base. Notice that I organized it by atom. And there's thiol with pKa of 13. And what functional group is this? This is the amine. So we look at our pKa table under amine. That is pKa of 38. Okay, so among these, which one is the most acidic? So of all these molecules, which one of these molecules has the highest acidity? Well, remember, it's going to be the molecule with the lowest pKa. So the most acidic would be the carboxylic acid at pKa 5, which is the lowest out of all of these numbers. Okay, now what's nice about the pKa table is it allows us to determine how strong an acid is. So if I give you a number of molecules, you can look at the table to figure out the pKa of all the different molecules, and then whichever one has the lowest pKa will be the most acidic. But let's say we wanted to determine not acid strength, but base strength. Now that's different. Do not assume the following. A lot of students think this: oh, if the pKa is low, then it's a strong acid. And if the pKa is high, then it's a strong base. That is false, okay? High pKa, all that means is it's a weak acid. It doesn't mean anything about what kind of base it is. To figure out what kind of base something is, we are going to use pKa, but in a slightly clever way. Let me show you. So using pKa to determine base strength. Okay, let me draw two molecules. Sorry, I didn't mean to zoom in like that on you. Let me draw two molecules and we will determine the base strength. And we'll figure out which one's a stronger base. Okay, here's molecule number 1 versus molecule number 2. Okay, so two molecules, we want to determine the base strength. In order to do this, we have to do a thought experiment, and we have to protonate both of these substances. So that's step 1, protonate. Oh, I forgot the negative charge on my second substance here. That's a formal negative charge. Okay, so we're going to protonate both of these molecules. Where are we going to protonate them? We're going to protonate them on the atom that's most likely to accept a proton. Remember, protons are positively charged, so that means they're going to go onto the negatively charged atom. If you don't have a negatively charged atom, the proton is likely to go on the most electronegative atom. So if we protonate each of these substances, we'll get this, and we'll get this. Okay, so that's just like pretending each of these is going to act as a base, and each one is going to gain a proton. Now, in their protonated forms, find the pKa's of the product that you just made. So, in other words, after you protonate, look up the pKa's of those products. In other words, find the pKa's of the conjugate acid. So if you look at the pKa of this guy, it's an amine. It has a pKa of 38. And if you look up the pKa of this guy, it's an alcohol. That has a pKa of 16. All right. So what that means is that the conjugate acid from the first molecule is a weaker acid. And for the second molecule, since the pKa is lower, it's a stronger acid. Now, because the first molecule produced a weaker acid, that means the starting base was stronger. In other words, the molecule that acid was derived by is strong, versus the alcohol, which was a stronger acid. That means it was formed from a weaker base to start. So in this way, we can use pKa to determine who is the stronger base. We just take the substance we want to assess, we protonate it, and we figure out the pKa of that protonated product. If the pKa of that protonated product is very high, that means the base was very strong. If the pKa of the protonated product is very low, that means the base was very weak. Does that make sense? Hopefully that makes sense. So what that means is that if you go the other way, it totally makes sense. Because if this substance is a stronger acid, then it's going to produce a weaker base when it loses that proton. And similarly, on the other hand, like conversely, I guess would be the word I would use. If you have a weaker acid, that is going to generate a stronger base. Think of it like this. If you have a really weak acid, it doesn't really want to give up its proton. If you have a really strong acid, it really wants to give up its proton. So imagine you have the strongest acid you can imagine. The strongest acid you can imagine wants to give its proton away. Once it gives its proton away, you're going to be left with the conjugate base. How badly is that conjugate base going to want to take back the proton it just gave? Not very badly. Remember, it gave its proton up because it didn't want it. So whatever's left behind is not likely to grab that proton back. In other words, what's left behind is a weak base. However, let's say that you have a really weak acid. A really weak acid doesn't really want to give up its proton because it's happy with its proton. If that weak acid were, by chance, to give its proton away, whatever was left behind might be wanting to take it back. So that means whatever's left behind is a strong base because it wants to rip that proton back that it just gave. So maybe, hopefully that kind of makes sense. So just the thing to remember is that if you want to use pKa to measure basicity, you have to protonate both of your bases and then determine the pKa of the two products. Whoever has the higher pKa of those two products, that was your stronger base to start with. We can talk more about this, but for now, why don't we stop right there and check out the quiz to try and put some of these problems into practice. Okay, bye for now.